and probably you're aware of what game theory is. We introduce it in a very simple way, very elementary. Then I will say a few words about neoclassical economics, that is the core, the core of, let's say, microeconomics in the way it is taught in our universities today. Then I will say a few words about macroeconomics and ecology. That is what I'm working on now with my team at Georgetown University. And then I will just allude to how we use stochastic calculus in order to test and to calibrate our models. But this will just be an allusion at the end.
And you'll have to got it, because I was just reminded by Steve to record this. So you have to got it that you accept the recording.
Oh, sorry. Yeah,
It's okay.
Sure. Okay. Is that okay?
Perfect.
So let us begin with, if this works, with game theory. And for that purpose, we will apply some real algebraic geometry, which sounds weird. What does real algebraic geometry have to do with game theory? You will see in a minute. So let me get rid of this. Oops. And also of this, which is here. So to understand non-coordinate game theory, it's a part of, let's say, applied mathematics that has been essentially invented in the late 30s, early 40s in the US, and a little bit later on in Israel. The idea is that you want to model a number of situations where you have a conflict. And the idea, the word game theory comes from the fact that many mathematicians used as a metaphor chess or any other game where you have a conflict, because each player wants to win, and both cannot win at the same time. So there is a conflict of interest. So a very simple way to understand the issue at stake is to look at this matrix here, by matrix, 2 by 2. You have two players, player A, player B. So player A chooses the column, either left or right, and player B chooses the row, either top or bottom. Now suppose that player B chooses T, top, and player A chooses left, then the payoff is the number which is in the matrix. So it's 1 for player B and -1 for player A. Now the question is, suppose I play with Michael and we know each other very well. We used to walk together in the forest, these kind of things. We are good friends, but nevertheless, each of us wants to win. So suppose I'm player B and Michael is player A, and we agree during lunch that we would play TL. Of course, thinking twice about it, Michael would think, well, I'm stupid. I should rather play right in order to win 1. Of course, Gaël will lose -1, but I'm selfish. So, but then I would think about it also twice, and I would think, well, I know that Michael is smart. So instead of playing left, he will play right. And if he does this, instead of playing top, I should play bottom. Because if I play bottom, I get 1 and he gets -1, okay? But thinking a third time about this, Michael would think, well, I know that Gaël is super smart, so he will guess that I will play right, therefore he will play bottom, therefore I should play left. But if I think this way about him, I will play top. So there is no fixed point in the process. So nobody knows who is going to play what. So if you just play in a deterministic way, there is no way to understand, there is no strategy which ensures you something that may help you win the game, okay? And actually this kind of dilemma was already known, maybe you know that, in the 17th century. So you have Blaise Pascal, the French mathematician and philosopher, who was asked to solve this kind of problem, and he could not, because he was stuck with this problem. The first guy who introduced a kind of quote-unquote solution to this is someone who is well known in real algebraic geometry. It's John Nash, the guy who was in the movie, A Beautiful Mind. So he was doing his PhD at Princeton, etc., etc. And after that, as you know, he got sick, he got a mental disease, and I met with him several times. And today, to be honest with you, he's definitely not able to do any mathematics, any kind of mathematics. He's just surviving with his schizophrenia. So what he did essentially is to say, well, the main problem in this game is a lack of convexity. We are looking for a fixed point in the mental process that Michael and I are following in order to understand who is going to play what. But for a fixed point, as you know, you need some kind of at least connectedness, or simple connectedness, if you're familiar with that, which in simple words would be, for instance, convexity. One way to reintroduce convexity is to add probabilities. So you will say, instead of playing either left or right, Michael will flip a coin, and with a certain probability, he will play left, with a certain probability, he will play right. And the coin might be biased, no problem. By doing so, you say, actually, the set of strategies that are available to Michael is the whole interval with one extreme point, which is left, and the other right, and every linear convex combination of both is possible. And then you recover convexity. And if you assume, in addition to that, that each of us tries to maximize the expectation of its payoff, then you have a nice linear convex problem. And here, in this very simple Milan example, the solution is easy. Each of us plays each strategy with probability 1/2. And that's the best you can do. And if during the lunch we agree, Michael and myself, that we are going to play 1/2, 1/2, each of us, then there is no way to change that. Nobody has an interest to deviate from the strategy profile we agreed upon, because that's the best you can do. Each deviation is detrimental to each of us. Is that okay? So this is what is called a mixed Nash equilibrium. A Nash equilibrium is a kind of fixed point where, suppose we agree on during lunch on strategy profile, nobody has any incentive to deviate from that. And it's a mixed Nash equilibrium because we use probabilistic strategies. Does this make sense? Mm-hmm. So this was an introduction to game theory in 5 minutes. Now, a little bit of notations. So you suppose that you have a finite number of players, I. Each player has a set of pure strategy, pure meaning deterministic strategy, Si, which for simplicity you assume is a subset of capital Rn. Then each player I has a payoff function, which maps the product of the strategies into R, the fields, and then you use mixed strategies. That is, you allow everybody to pick a probability on the simplex over his or her pure strategy set, and you say that sigma star is a Nash equilibrium if for every player and for every deviation that is based on a strategy that this player could play, if he plays sigma I instead of sigma I star, he will not increase his payoff or the expectation of his payoff. So nobody has an incentive to deviate. Okay. So equipped with that, you understand that in the 50s, the main question was, is it possible to solve any game, at least any finite game, finite meaning that every strategy set is finite and there is a finite number of players. And if possible, this would be, the dream, the grail, is it possible to have a concept of equilibrium such that you have a unique outcome for every game? And the disappointing answer was certainly not a Nash equilibrium. Why? Because if you look at this very simple game, you have at least 2 pure Nash equilibria, even without mixed strategies, which is T2, and 1,1. If for whatever reason we agreed with Michael during lunch that we would play 1,1, nobody has an incentive to deviate from that. We cannot deviate from that. Okay, so it's a Nash equilibrium. It's a stupid Nash equilibrium because had we agreed on playing 2-2, everybody would be better off. But that's it. Okay. So the other consequence of that is that the concept of Nash equilibrium does not embody any kind of cooperation. In order to prefer 2-2 to 1-1, we need this, the slightest amount of cooperation between each other. We need a kind of, non-completely selfish understanding of the way we plan to behave, but that's not encapsulated in the very concept of Nash equilibrium. So, and you can also think of it in terms of what economists call Pareto optimality. So Wilfredo Pareto was an Italian sociologist from the early 20th century, and he, for the first time, invented this very simple definition, which is the following. Suppose we want to share a cake, a Sunday lunch with the family. You have the kids, everybody's there, you have a big cake, but this big cake is such that part of the cake has lemon, part of the cake has chocolate, it's a weird cake, heterogeneous cake. So some of the kids prefer chocolate, some others prefer lemon, whatever. And then you have to divide the cake between the members of the family. So suppose you have reached out a partition of the cake so that you give it to everybody. And then your beloved nephew says, hey, I have a better distribution of the cake so that nobody loses anything in terms of, pleasure. And at least myself, I'm better off, strictly better off. This means that the first allocation was not Pareto optimal. So an allocation of whatever payoffs, pieces of cake, whatever, is Pareto optimum if there does not exist an alternate allocation respecting all the constraints, which is such that nobody loses and at least one guy is strictly better off. Okay. So now using this, you see that there is at least one Pareto optimum here, obviously, which is 2-2, but which is definitely not the unique Nash equilibrium of the game. So some Nash equilibria are stupid and non-Pareto optimal. Okay. And in addition to that, you have the indeterminacy problem. That is, there is no uniqueness. No way, no hope to have uniqueness. So some game theorists in the 80s even invented an even broader concept, which is called the correlated equilibrium, where instead of asking everybody to choose a probability on the pure strategy set, you take a probability on the product of the strategies. For instance, you say, let's play with probability 1/3 2-2 and with probability 2/3 1-1, which means we have a stochastic correlation device between Michael and me, but let's say we flip a coin, but according to the outcome of the coin, then either we play 2-2 or we play 1-1, which we cannot play if we are completely independent. Okay, and of course, obviously, the correlated equilibrium concept encompasses every Nash equilibrium, but it's even much broader than that. So you may have correlated equilibria which are not Nash equilibria, etc., etc. So the situation is even worse. You see, so people were kind of desperate and looking for kind of structure. So then they said, well, you know, this is because we are focusing on one-shot games. That is, we have the fiction that, you know, you play chess once, which is not true. Actually, it's an extensive form game where time unfolds, and by taking explicit account of time, maybe we can narrow, you know, the set of Nash equilibria, which makes sense. So then game theorists use this type of representation of a game. Suppose now there are two players, 1 and 2. Player 1 chooses the first one of the two branches of the first node, and player 2, depending upon where he or she is, chooses the two following branches. So now to understand who is going to play what, obviously, suppose you are player 2, and suppose you are on the left here. Then what will you do? You will obviously choose A in order to get 5. Okay. And if you're on the right, you will obviously play A again in order to have 2. Knowing this, player 1 will have to choose between playing F, in which case he knows or she knows he will get 5, or playing U, in case he knows or she knows he will get 8. So he will play U, obviously. Very easy. Then you see that implicitly by saying this, I was using some kind of refinement of the Nash equilibrium concept. What I just said, saying, well, start from the end of the game and then you go backward, you know, along the tree of decisions. This is stronger than just a Nash equilibrium. I don't have time to go into all the details, but there are such backward induction equilibria, which, I mean, all of them are Nash equilibria, but there are Nash equilibria which are not backward induction proof, if I can say so. Okay, so now we are going in the other direction from correlated equilibria. Correlated equilibria are a broader concept than Nash equilibrium. Backward induction proof equilibria are a smaller concept. So then, starting with this, a number of game theorists try to refine more and more the concept of Nash equilibrium, starting with this, so backward induction proof, which is called sub-game perfect, and then to have something which might hopefully lead to some uniqueness, and why not to some Pareto optimality. You see the program? And why are they obsessed with that? Because of the invisible hand. You know, the old story of Adam Smith in the 18th century, in his book Wealth of Nations. You know that Adam Smith was an Irish guy from Glasgow, a philosopher teaching moral philosophy. So he had no clue about economics, but he wrote a book in economics. You know, and he said in this book, he wrote a very famous paragraph saying, "It's not generosity or empathy of my butcher which allows me to get the meat I need. Is the invisible hand of the market. Supply and demand, blah, 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 all this, you know? And so economists used to think of this in terms of when you have decentralized people interacting on a market, the quote unquote invisible hand should drive them towards a Pareto optimal allocation of scarce resources. Whether this is true or not is another story, but that's the kind of legend that we keep repeating in our courses in economics. So game theorists had the idea in the 50s, we are going to provide a sound foundation, a mathematical foundation to the invisible hand. Bad chance. No, really too bad. I mean, it says exactly the opposite. You have an indeterminacy of equilibria, and some of them are not Pareto optimal at all. So what do you do with that? It's a mess. You see the point? So having this program in mind, they went even further and they discovered, there are situations which are so you can play with the game over there to find the subimperfect equilibrium of the game. You can also play with this one. We don't have time to do this. The dots here mean that the first move of player one is hidden. Like when you play cards, you play something, but your opponent doesn't know what you did. So player two, when he or she will play, she doesn't know whether she is here or here. So this complicates a little bit the game. I left you, it's funny to try to find the solutions, etc., just to give a flavor of what we're doing. So essentially, now math is entering the picture. In order to find a concept of equilibrium which makes sense, game theorists had to rely on fixed point theory. Because as I told you, you remember the mental process we were undergoing with Michael. What about if he does this and if I do this, how will he react? If we reach a fixed point in this process, then we are done. We have reached a strategy profile from which nobody will have an incentive to deviate. Okay? So mathematically speaking, you have to look for a fixed point. And as you know, the Brouwer theorem tells you at least you need some kind of simple connectedness. That is the fact that you have a map which needs to be continuous, no doubt about this. We find on a set C, which will not be convex, but which must not have a hole in itself. Because as you know, otherwise you can take the rotation, which is continuous, and which has no fixed point. Okay, that's very, very easy. So that's known as the Brouwer fixed point theorem. So now what they had to do is that the expectation operator is just linear. It's not strictly concave. So you cannot hope to have uniqueness like in a function. You look for the fixed point of a function, like in the Brouwer fixed point theorem. You need to look for the fixed point of a set valued map, which is slightly more complicated, not that much, but. So then you need to rely on something which is known as the Kakutani fixed point theorem, which is the same as the Brouwer fixed point theorem, except that you deal with the domain, which is again, let's say convex or simply connected. But now you deal with the correspondence or set valued map, which takes convex compact values and which has to share some generalized version of continuity in order to make sure that you can find a fixed point. Okay? So there is one version, it's this one. If you have upper Himai continuity, then that's fine. We find a fixed point. If you have just lower Himai continuity, which means that you can find a sequence of points in the image whose limit is not in an image of anything, like here, because it's an open set, then you may not have any fixed point, which is very intuitive. Just have to write. Okay. So then game theorists had to rely on these kind of extensions of the very famous fixed point, Brouwer fixed point theorem. But this was not enough, because this was just a way to ensure existence. And as you know, existence is not a big deal for game theory. The big deal is Pareto optimality and uniqueness. So they were looking for more structure of the game in order to gain some information about how they could reduce the problem in such a way that they would get the big grail, which was uniqueness and Pareto optimality. And for that purpose, they used some real algebraic geometry. So for that purpose, I just remind, I'm sure most of you know this, what a semi-algebraic set is. So suppose we are in the field of real numbers to simplify things. And a semi-algebraic set is just a set like capital A that can be written as a finite intersection and or union of a finite number of polynomial equalities or inequalities. So an easy example is this equation over there. So the graph of this function is obviously semi-algebraic, but the graph of this function is not. The graph of cosine is not, because cosine cannot be expressed as a polynomial. So, and logarithm either, exponential either, etc., etc. So semi-algebraic sets are kind of very simple sets that can be reduced to intersection and union of polynomial equalities and inequalities. Okay. And then there is a very, I mean, the first time I saw this as a student, I was, amazed. So that's why I'm telling this to you, especially for the students here. That's the big mathematical program of having a kind of translator between logic systems on the one hand and geometry on the other hand. I mean, Grothendieck, whom we were alluding to a couple of minutes ago, had this kind of program in mind. I mean, algebraic topology or algebraic geometry essentially is an attempt to have a correspondence between algebraic objects like groups, rings, fields, etc., and geometric objects, like weird manifolds, with corners and it's kind of messy things. So here it's almost the same. The Tarski-Zeidenberg theorem is a translation between logic and geometry. And it says every semi-algebraic set can be expressed with a first order formula of the theory of the real numbers. What is it? It's a formula which uses, the quantifiers over there, there exists logical connectives and or negation, the four operations equal, bigger than, strictly lower than. Okay. So if you can write a formula with this on the real numbers, that's a first order formula. And the Tarski-Zeidenberg theorem tells you the set which is defined by this formula must be a semi-algebraic set. Very easy, very simple. So once you have understood that, it's very easy. You spend your entire life checking whether this or that set is semi-algebraic. Very easy.
So is the idea that these things lead to polynomials, and on the other side,
that's
finite unions?
Exactly. That's the surprising thing. That is that you have naturally polynomials emerging from these kind of apparently completely uncorrelated questions. So once you have this, you can take advantage of the fact that that semi-algebraic sets have a very rich structure. And that's funny because John Nash, the guy who invented, what I told you about game theory, is also the same guy who invented the Nash manifolds. Nash manifolds, as you may probably know, are differential manifolds which share this type of structure like a semi-algebraic set. But probably he himself was not aware of that. He never made the connection between both aspects of his own work. That's funny. He became sick before that. So, so maybe one way to understand that is to tell you this, the famous Sartre theorem, which is usually taught in differential topology or differential geometry, which tells you that if you have, so suppose that's just an example. Suppose you have the graph of this set-valued map here over this domain here for simplicity, and you look at the projection. You project over the first coordinate. So the projection obviously is a smooth map, no problem. And the projection is such that you have a number of critical points where the projection will not define a homomorphism locally, which is this point here and this point here. Okay? And that's very interesting because that's known in a completely different branch of mathematics as being catastrophe theory. You suppose that you are moving the parameter here, you are following the point which is on the branch on the top, and then when you reach this here, suddenly you are moving like here, then it's a catastrophe. You may have catastrophic events. So catastrophe theory in the sense of René Thom, the French mathematician, is the study of this kind of the geometry of these critical values of smooth maps, essentially. Now, what is
the catastrophe? I mean, is it like three images coming together?
Yeah, exactly. For instance, you have two images coming together.
Separating.
Yeah. For instance, yeah. So suppose you are here.
Yeah.
Then if you look at the images, you have three images.
Yeah. And two of them come together.
Here, yeah, exactly. Now you have two. And if you move infinitesimally to the right, you have only one.
Yeah.
So that's a catastrophe. You see? And so what Sartre's theorem tells you, the famous classical textbook Sartre theorem, is that if you look at the images of these critical values by the smooth map, which is a projection, then they are of measure zero. They are negligible. Okay? But as you know, being of measure zero does not mean that you are dense in a topological sense. There are famous counterexamples of sets which are dense, but not of complementary with measure zero and vice versa. That's not the point. That's not the case for semi-algebraic sets. They are nice sets. They are the sets that we students love because for them, these kind of pathologies disappear. So for a semi-algebraic set, whatever being your understanding of genericity, it's the same. So for a semi-algebraic set, being a full measure or being topologically generic, meaning you contain the countable intersection of open and dense subsets, that's genericity, no? Or just the fact that you complement, the complementary set is of strictly smaller dimension, all this is equivalent. So all what we have in mind when we study topology for the first time, and let's say these kind of weird counterexamples in topology, they disappear with semi-algebraic sets. So these are very nice sets.
Is generic the same as closure equals the whole thing?
So what you think, you are thinking about topologically generic. So the definition would be you contain a countable intersection of open dense sets, which means indeed that each of these open dense sets is such that the closure would be everything, would encompass the entire set.
But the set itself is completely defined by the countable set of densities.
The
Every
set
point.
itself could be larger than that.
Okay,
Yeah, you just need to contain it.
got it.
Now, for instance, there is a nice theorem. So in real algebraic geometry, which tells you if you have a map between two semi-algebraic subsets, which is itself semi-algebraic in the sense that the graph of the map is semi-algebraic, then there exists a generic semi-algebraic subset of the domain, which is such that the map, the restriction of the map on this generic subset is smooth, which is certainly definitely not true if you forget semi-algebraicity. So which means if you deal with semi-algebraic objects, generically, they are very smooth, very nice, So there are things you can do with semi-algebraic subsets you can never do with standard functions that you use, in analysis. You see, so that's a nice aspect. And then, of course, then game theorists, some clever game theorists discovered, and they were very happy with that. Oh, but the Nash equilibria of the finite game are all semi-algebraic subsets, and all the objects that we use in game theory, when restricted to finite games, are semi-algebraic. And therefore, they got all, they could import all the richness of what we know in real algebraic geometry about these nice subsets to game theory. So they knew, for instance, that the set of Nash equilibria has a finite number of connected components, like the one that we saw here. Remember this very simple example. Here, yeah. So here, obviously, you have 2, 2, you have 1, 1, and if you look at correlated equilibria, you have just the convex interval linking the two. That's the connected component. Very easy, okay? So, but of course, it may be much more complicated than that, but nevertheless, you can do some geometry because you have a finite number of connected components. Each of them is a smooth manifolds, and you are in a known land to do some nice geometry. So then we could enter further into what people did in using algebraic geometry in game theory, but it would become then very complicated. The end of the story is that in the early 2000s, there was a series of very nice papers written by a very good guy who passed away meanwhile, unfortunately, from Belgium, who went up to the end of this intellectual program trying to refine the Nash equilibrium concept in such a way that it would lead to something which is Pareto optimal and unique using algebraic geometry. And the conclusion is that's impossible. So he did not just prove that he did not do it, but that nobody would do it. So you necessarily have a set value equilibrium concept. So you have to forget completely the deterministic Laplacian. You say that in English? Laplacian, metaphysics. That if God knows all the preconditions, there is a unique, way for the world to go further. Okay, Laplacian uniqueness, because in game theory you are stuck with indeterminacy of Nash equilibria, whatever being the kind of refinement you are looking for. And in addition to that, there will always, it's easy to find games for which some Nash equilibria or some refinements of Nash equilibria will not be Pareto optimal. In other words, the invisible hand is invisible because it doesn't exist. Okay? So, okay.
Who is the author?
Jean-François Mertens, Mertens. I can send you the papers. Yeah, these are beautiful papers. But to be honest, I think 1% of economists have read them because it's tough in terms of geometry. So they don't read that. They pay, they honor the paper, but they don't read it. So the next point, the next application. So does it make sense, especially for the students, as an application of algebraic geometry, which is surprising? I mean, I remember honestly when I was a student discovering this, I said, wow, you would not expect that in economics. So the next thing I want to present is differential geometry. So it's more classical mathematics, but it's very interesting. It's a very interesting result. So in a standard course in microeconomics, the prof would begin by saying, suppose you have a finite number of households in your economy, let's say the US. Each household is equipped with a utility function UI, which maps the set of baskets of consumption goods that he or she might want to consume, like a TV screen, like, a Netflix registration, or an ice cream and a pizza. And then UI maps this set of things into capital R, describing your degree of affinity, as we say, the pleasure you take from consuming your pizza. Okay. And of course, if it's increasing, this means you have more pleasure. So of course, we are going immediately to suppose that UI is smooth, concave, increasing, that there are only a finite number of commodities, and that you have an initial endowment, EI. That's the portfolio you inherit when you start your life on the market. So your parents had some pizza, some ice creams, a TV screen, and all these kind of things, and you come with this, and you want to share. Let's say you observe that you have a pizza which is a margarita, and it turns out that Michael has a pizza which is a primavera, which is better. You prefer primavera. So you want to trade margarita with primavera with Michael. But there is a point.
Why are these functions increasing?
Oh, they assume that if you increase the number of pizzas, you are, more the better. I know.
At some point you get full. But yes, let's not ignore that.
I used, when I was teaching this a long time ago, I used to tell my students, I used to take the worst singer in France, and I was saying, well, suppose you increase the number of CDs of this singer you have in your room, are you sure you'll be very happier? And so then they understood, suddenly.
Yeah.
Because a pizza for a student, no, I'm kidding.
No.
You see what I mean? So
Jeff said he wouldn't assume that.
okay. And of course, there is a price vector P, which tells you how much you have to pay for each commodity, for the pizza, the screen, etc. Then what each household is supposed to do is to find a vector of commodities, xi, in capital R at the power of L, which maximizes its utility, or his or her utility, subject to what the budget constraint, that is the price of the commodities I'm going to consume, cannot exceed the price of my own portfolio. Because I'm going to trade with Michael, one pizza against the other. And of course, I can afford to buy only what I can get with what I sell. Okay, so given the conditions I took here, that's a nice convex optimization program. And so microeconomic theory became with this. Then what they say, these people, is that suppose you write di of p, which is the argmax of this maximization program. So that's the demand of player I, if p is the price, and you ask that the sum of the demand be equal to the sum of the supply, which is the sum of initial endowment. So the equation over there is the equilibrium condition. If you have this equation, it means demand equals supply. Okay, so that's the basic market equilibrium condition. Just to give an example, a flavor of why this is so important, because microeconomists and neoclassical economists use this assumption everywhere. So they start by assuming that every market is at equilibrium to begin with. Just as an example, that for the Paris Agreement in 2015, every country had to be nationally determined. And you see, roadmap describing how this country plans to decarbonize its economy from this time, 2050 towards 2030. So this one is a model, a big new classical model. And since this had been partially funded by the French National Bank, where I saw the certificate, but it's not that. It's not. So it's hard. So I said, so we had an possible to change the Chinese bank, the American. So I think I'm nice to have a model.
Hold on, just turn my microphone isn't working. Sure. Steve, in here. There we go. Steve, here. Just severe static in here, saying. How about now? Still bad. Trying to see. No. You mean you can hear that? That means you can hear. Steve. I don't know. Trouble for me to hearing feedback. Getting worse. You know what? Let's try and do something. Why don't you change it to your regular to the max.
Okay. Can you hear me now?
Much better.
Are you guys able to hear me at this point? Yes.
Okay. So I should remain close to the computer.
Remain close to the
Okay.
computer, yeah. Yeah, much better.
So what I said to the beloved colleagues is that, you know, your model is very sophisticated and I'm very impressed. The only concern is that suppose that in order to implement your roadmap, you need like 80% of unemployed people in China and 400% of your GDP as public debt. We know you will never do it because that's politically unfeasible. My only concern is that you will never see it in your model because that's impossible. It's a built-in assumption that this will never happen. So I'm wondering whether this model is really useful, I said. So the American guy was very upset and he said, wow, you're right, but it's very easy to add debt and disequilibrium in the labor market, which is absolutely not true because if it was easy, he would have done it. And the Chinese colleague said, you want some more tea? So the Chinese guy was much more clever. So, but this gives you an idea of where we are as economists, you know? This assumption, which might seem innocuous, actually is leading to questions which are completely crazy to my mind. So,
So wait a minute. This is actually something I often wanted to ask you about this.
Yeah.
Here I have some of those. Is there any notion of what the dynamics ought to be? This is the equilibrium of.
yeah. So actually, no, not in neoclassical economics. There have been some attempts by someone you know, Stephen Smale, the guy who got the medal Fields, not the Fields medal. So he tried to write some differential equations that would lead to this equilibrium, but it's not completely. It's very clever, very nice, beautiful mathematics, but from an economic viewpoint, it's not really convincing. But it's not based on what's happening in real life. So it's a purely intellectual, theoretical attempt, which is nice, but which leads to nowhere when you try to understand, you know, now we have inflation in the US, how come, what is the bargaining process that leads to that? You cannot use Steve Smale's dynamics for that. It's unfortunate.
This is an open question.
No, because what I'm going to show you now is the answer to that, but that's a third point.
The answer is no.
Yeah. And actually, I started a long time ago, but still by studying what Steve Smale had done to try to build on that, and then I had to give up because it was beautiful, but you know, not so. So then many economists would say, well, you know, I mean, markets are at equilibrium to begin with because why? Because we have this curve of aggregate demand, we have this curve of aggregate supply, and if they have the right properties, they intersect at one point that's unique. And in addition to that, we can prove to you that this equilibrium is Pareto optimal. So, and this was proven in the 50s by someone you know, maybe the way in the US with John Kenneth Arrow, who got to Nobel Award. So, in fact, the French mathematician, Giraud, who was in California at this time. And then they're happy with that. And they tell me, well, there is no unemployment. Because
They're saying as you move.
okay. Because the labor market is at equilibrium. The unfortunate thing is that this is not true in the sense that, what about if I was to tell you that the market demand curve does not slope downwards? What about if I was to tell you that aggregate demand can be any polynomial? Then of course, imagine that if the demand function is no longer downward slope like this, but is any crazy polynomial, the graph of any crazy polynomial, you may have multiple equilibria, non-Pareto optimal equilibria, no equilibrium at all. Everything is possible. And is it true that what this guy Morpheus is now saying? And the answer is yes. And this has been proven by Debreu himself. So that's very unfortunate. And this is where differential topology enters the picture. Why? First, because you observe that if you look at this maximization program here, then you see that it's homogeneous of degree 0 with respect to prices.
Can I ask a question?
Can
I ask a
multiply prices
question
by
here?
2, doesn't change anything. Okay. So which means you can normalize prices, and suppose I want to normalize them in the unit sphere, but they need to be non-negative. So I'm taking just the non-negative part of the unit sphere, which is perfectly possible, which is written over there. And then I observed that the aggregate excess demand function, which is over there, that is the sum of the demand function minus initial endowments, is orthogonal to the price. Why? Because people fulfill the budget constraint very easy. So this function zeta over there is a vector field on the unit sphere. And then the question becomes, are there structures imposed by the fact that this vector field is not any vector field, but comes from the maximization program of a household, blah, 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 blah. Does this imply something on the vector field?
So, Nimai, do you want to ask a question?
Yeah, I don't know if he can hear me. Is he able to hear me?
Sorry? Yeah, that's the point. So I have put this, give this example. So 0 of the vector field is an equilibrium. And the question is, how does, like the geodesics or any solution of this vector field converge or not to this point? This was roughly the idea of Stephen Smale at this time. But then I have a more basic question, which is just the vector field itself. Does it have enough constraint so that we know something about the equilibrium? And the unfortunate answer is that no, any inward on the boundary pointing vector field, which is continuous on the unit sphere, can be the aggregate excess demand function of a well-chosen underlying economy. In other words, everything is possible at the aggregate level. So this has been proven by 3 guys at the same time: Sonnenschein, a German guy, Mantel, an American guy, and Debreu, the French guy, at the same year, 1975. And after that, Debreu, who had got the Nobel Award meanwhile, stopped doing any research because he had understood his old theory cannot be falsified because you cannot predict anything at the aggregate level.
So he destroyed economics.
Yeah, exactly. He had destroyed his own economics. So when I was a student, I knew him. So he came to the seminars at the ENS. I don't know whether you know the ENS, Economic Superior. And he didn't say anything. So he was completely mute. And everybody was, very impressed, thinking he must think very deeply about something very profound. And I think, no, he just gave up completely. So this was really, some kind of weird situation for him, I guess so. So this is where, in order to prove what I just said, so the Sonnenschein-Mantel-Debreu theorem, you need to involve some hard topological, differential topology. So just for the students, this has something to do with the very well-known Poincaré-Hopf theorem. I don't know how you call it in English, which is that here, since the positive part of the sphere, the unit sphere, can be contracted into one point, thanks to some homotopy, then you are sure that the vector field will have a zero, must have a zero. It's the same reason why you have hairs, on your head. If your head is topologically equivalent to this, which don't obey to you, same problem. It's your hair are a vector field, and there must be a zero somewhere. That is, a hair which is orthogonal to the tangent plane to your head. Okay, so these kind of ideas allow them to destroy neoclassical economics. So then this leads to, is there an alternative to that? And the answer is yes. And the answer is yes. And this is what we are working on at Georgetown University, my team. The starting point being that, in the past recent years, more and more macroeconomists realized how wrong they are. So one example is what happened with Greece. I don't know whether you followed what happened with the crisis of public debt in Greece between 2010 and 2015. So you have here the evolution of the GDP of Greece between 7 and 11, and it was worse in the following years. And then you have the predictions of the IMF. So each time the IMF is completely wrong. So the people in the IMF are not stupid. I can do this. They are more clever than I am. The point is that they use equilibrium models, which tell them whatever is happening, the economy of Greece will go back to its previous equilibrium. So listen, each time it goes back, and since they have just this kind of tool to predict anything, they just repeat the same mistake year after year, which makes, I guess, this prediction completely useless. You see? No, they never succeeded. Well, I mean, the GDP stopped falling down in 2015, right, and then reached a plateau. So maybe they were right at the plateau. Yeah, you're right. I should be fair. No, you're right. I should be fair with them. When everybody is dead, they are right. No, I'm kidding. But another example is the predictions of the price of oil by the International Energy Agency.
Let me bring one question that just came up. Your questioning of the market equilibrium and the downward sloping demand curve reminds me of the Cambridge debates between MIT and Cambridge.
Oh yeah.
Economists.
Yeah.
The controversy got up because the critique failed to establish empirical significance of the results. So the question is, what empirical practical significance of a downward sloping? What is the empirical practical significance of a downward sloping demand curve? In ordinary terms, such a curve would mean I'm more willing to purchase more pizza when the price of pizza goes up. How common is that?
Oh, that's perfectly possible. This happens every day. You have a number of items of commodities that people want to buy because they're expensive.
Yeah.
Look at cars, etc. You can also think of
expensive colleges.
Yeah, expensive colleges. I mean, yeah, cars, colleges. But you also the fact that, for instance, suppose you rely both on oil and gas. You have a war in Ukraine, and you used to buy your oil from Russia, and you can no longer do this. So you need more gas. It might be the case that the price of gas is increasing, and nevertheless you are going to buy more gas because you cannot buy oil. So yeah, okay. Yeah, exactly. So that's another example of a problem that we have, which is that we are completely unable to forecast the price of oil. So here you have the rate curve. Here is the true price curve, and each time you have prediction of the International Agency. Another example of a problem that standard macroeconomists are facing is the very simple idea that if you increase the quantity of money circulating in the economy, you should have inflation. I'm sure you know that. So this is the quantity of money printed by the Fed just after the great financial crisis. So you see here QE1, the quantitative easing 1, QE2, QE3, and now because of Ukraine, there is a QE n+1. I don't know how much n is, but anyway. So a huge amount of money has been printed by the Fed, and the rate curve is the consumer price index in the US. No inflation at all, nothing. So that's a problem for many models. Another problem is also the fact that usually when a country increases tremendously its public debt on financial markets, the spread, that is the riskiness of this debt, should increase. That is, people should ask to be more paid in order to lend to this country. So here you have the red curve, which is the public debt of the US, and you have the spread of the US. The spread is declining. So these are paradoxes that standard models are not able to deal with. So what we're doing, we are relying on dynamical systems, nonlinear dynamical systems. To the best of my knowledge, the first who did that for a seemingly economic model was Meadows, at MIT in '72 in his famous report to the Club of Rome. So he used this kind of simple model, actually. Maybe I have, yeah, that's the true complete model, which has just, nonlinear back loops. So the principle is very easy. And we are essentially doing the same. Just incidentally, you might be interested in knowing that, so Meadows, this beautiful book in 1972, and which, there were, I don't know where you know this report, you're familiar with it, but there were 10 scenarios. Scenario 1 and scenario 2 were leading to a big collapse at the world level, and 3 to 10 were various scenarios that avoid the collapse. Now, in 2008, for the first time, and then they did it again in 2014, there is a physicist from Australia, whose name is Graham Turner, who then did it again in 2014 in Harvard. He backtested the scenarios of Meadows, saying, well, we are now 30 years later, we can check whether one of the scenarios was correct. So he did this backtesting. The good news is that he found that 2 scenarios fit very well with the curves indeed followed by the planet meanwhile. This is good news because if you do the same kind of backtesting with standard macroeconomic models, which are always at equilibrium, after 2 years, they are completely wrong, but just completely wrong, honestly. The bad news is that these were the first 2 scenarios. Yeah. So we are doing exactly the same kind of things. So very quickly, we start with the skeleton of the economy. That is, we start with the accounting metrics to make sure that, it's like the first law of thermodynamics. We want to make sure that no money disappears or whatever, which is far from being obvious in standard economic models. So here we take care of the stock flow consistency of the model. And then we add some differential equations. So since time is running, I don't have time to enter into all this. I will jump immediately to the conclusion. And so we end up in the simplest case with a three-dimensional dynamical system with 3 variables, state variables, which are omega, the share of wages in GDP, which, as you know, is declining now for decades in industrialized countries. Lambda, which is the share of employment, which is definitely not equal to 100%. And small d, which is the ratio between private debt and GDP, which is exploding now in a number of countries. Sorry? Oh, yes. Sorry. And so we have the 3-dimensional dynamical system. And as you know, above 2, we enter into the beautiful world of chaotic systems, potentially chaotic systems. So indeed, as soon as we add some lag somewhere, we end up with some chaos. So so I plan to try to understand better these chaotic properties, but for the time being, I don't succeed in. But then, so we have these kind of things. Essentially, this family of models of dynamics have 2 long-run equilibria. One of them is a satisfactory equilibrium. The other one is a catastrophic equilibrium where nobody works at the end of the day. And of course, then the question is, do you know the basin of attraction of each equilibrium? Are they locally stable? Is the economy going to converge to one of them or to loop? Do you have limit cycles? And all these kind of beautiful questions you can ask once you have a nonlinear dynamical system. So this is a very simple example. It's a theoretical example where the economy starts here loops. So you have an endogenous periodic cycle at the beginning. Small d is the ratio between private debt and GDP. So that is increasing, and then it plateaus, and then you converge towards a nice long-run equilibrium. That's just a theoretical example. And then, of course, you can numerically simulate the Bayesian of attraction, start the Bayesian of attraction of an equilibrium, etc., etc. So we use these to couple these kind of macroeconomic models with climate, and then we ended up with this following these kind of results, which have been used in the Stern-Stiglitz report, Nick Stern and Joe Stiglitz, because I was member of the commission. So absent any climate change, the world economy would converge to an isoequilibrium. So we are not Marxist, as you see. But now if you add climate change, then we may have big collapse before the end of this century, in the same spirit as what Meadows did. And that's possible because it's not a built-in assumption that collapse is impossible. You see, just as simple as that. Very interestingly, I believe, is that climate change pulls the economy outside of the Bayesian of attraction of the good economy. So you can see it here. The economy starts here, moves towards the good economy, and then at a certain point, climate change is destroying so much. But in this example, the forces of climate change are not strong enough to prevent the economy from converging again. And here, it's not the case. This time, the economy is stood up and converges to a catastrophic economy. Okay? Yeah, question.
Oh, well, this is a little different question, but you mentioned the error between
Yeah.
that the preferences are fixed.
Yeah.
Or given.
Yeah.
Suppose that people can choose their
Yeah.
preferences. Can you still extend analysis here?
You mean the neoclassical analysis or this one?
Or this one I know about.
Okay, the neoclassical analysis.
Neoclassical and the national.
Yeah, the national. Yeah, it's possible. This has been done already. But yeah, it's possible because the point is that according to which criteria you're going to choose your preferences. So you are just increasing the level of, implicitly you have to add new preferences on preferences. Otherwise you cannot solve any maximization problem. And then you end up with the same problem. You are just making the set of preferences more sophisticated, but it doesn't change the problem. You see?
Okay, if that is possible, suppose human preference has evolved over time.
Oh, that's another question,
Right.
which is well known.
Suppose
Yeah.
evolved, okay. And how would the people choose their preference?
Yeah, so empirically speaking, we don't have any theory of that. As far as I know. That's a well-known question, especially for the calibration of macroeconomic models, where most of these models assume that people keep the same preferences from 1950 to today, which of course is not true. So sometimes when people are sophisticated in math, they try to find some bricks, statistical breaks in the statistical meaning of the word. And then they say, well, in the 80s, usually it's in 70s, 80s, people have changed their mind about what's worth consuming or not. For instance, with oil, after the second big shock, there was really a change in the 80s, in the early 80s, with regard to oil. So people have switched from oil to anything else during a few years. So then you see there is a change in preferences. But then for oil, it's easy.
That is a change of preference. It has changed the choice, not
Yeah.
preference from itself.
But then that's
because of
yeah.
change in relative price, so that they decided to change from oil to.
Yeah, maybe you can say that. But if you change your preferences and you don't see it in your demand, then to a certain extent that's metaphysics. That is, I can say, well, my preferences have changed, but my demand is the same. Then if it's the same for an economist, you have the same preferences. You see? You have to observe the change. So you have to see the demand which is changing. Otherwise,
I think I would say ask a more specific question.
Yeah.
Like some computer game companies make the game such that people can be addicted to it.
Yeah, sure.
If they know the preference of people, they may design such a way that people
Yeah.
are addicted to it.
Yeah.
Is it moral, immoral, illegal, or illegal? What should be?
Oh,
Because it's your choice,
sure. I'm strongly against that. But as a personal guy, as a citizen, yeah, I think this destroys democracy. We have the same problem with social media. Oh, yeah. And this is why we had Trump. I mean, at least partially. You know, I say this as an outsider, being French, but yeah, it seems to me that's a big threat on democracy. That's why a number of people here in the US want to regulate social media. No, and there is this idea that we should have an internet 3.0, which is really decentralized, not in the hands of a few mega companies, you know, including social media, because otherwise they can just play with us. And they enforce the tribalism, we say that tribalism of the American society and the polarization of the society, which in the eyes of a French guy like me is just crazy, you know. The fact that there are still people who believe that Putin is a good guy today in the US, you know, it's a little, you know. And I'm told that this is the case, no? You can confirm. I don't know. Some Trumpists in the Midwest who still believe that Putin is a good guy, or that Trump won the elections, or that, you know. Should I jump directly to the fourth theme and then we discuss?
Yeah.
Okay. So the fourth topic, yes, and then what we did is that we plugged this kind of macroeconomic model with true climate models. And standard economists cannot do it because you cannot put an equilibrium model with a dynamical system. A climate model is a dynamical system by construction. So we can do it. And so we have, to the best of my knowledge, the first simulations using a real coupling between, I just show you this to make our students a little bit afraid. So if we don't do anything along the business as usual scenario, that's a picture of the Earth at the end of this century, where the color is the number of days where people will be exposed to lethal combinations of heat and humidity. So if it's dark red or brown like there on the Amazon, it means in the US, you see it's yellow. Yellow means 1 day over 3. So 1 day over 3 in the southeastern coast of the US, people will be exposed to lethal combinations of heat and humidity. And you cannot save yourself with air conditioning because air conditioning is increasing the problem, as you know. Same story for China. It's even worse. It's even worse in China. Look at eastern coast of China over there. Not mentioning, let's say, Indonesia, which is dark red, partially, and which is the most populous Islamic country in the world. So this is what we want to avoid, definitely. Okay. So using the kind of model that we are using, we try to understand alternative scenarios which avoid such a kind of disaster. That's why I'm going to present this to the Congress next month, because there are a number of politicians who are interested in that. So the last point I wanted to mention has to do with stochastic calculus. I'm sure you are not all aware of the beauty of the Brownian motion. And it turns out that we need this in order to calibrate our models in macroeconomics for a very simple reason, which is that in macro, the highest granularity that we can have on empirical data is quarterly. So we have only 4 points per year of data. That's not enough, because then you have a small number of points. And as you know, as soon as you have a small number of points, this is becoming a problem to do any type of statistics. So either you rely on what James Heckman did, which is a possibility, but it's not a solution for us in macro, or you do what one of my PhD students did. He introduced Brownian bridges. The idea is very simple. So you have a few discrete points, you add a Brownian motion, you simulate a Brownian motion between 2 points. You impose the first, the beginning and the end, and as you know, the Brownian motion is a white noise. But the beauty of that is that it provides you with a continuous time process where it's way easier to do some statistics. So I just wanted to mention this as I think a very interesting example of the use of stochastic calculus, even in macroeconomic models, which are entirely deterministic. You know? And I will stop here so that we have time to discuss.
Well, please, first clip. Open it up for questions, and I'll type in the questions in case people can't hear.
So it seems to me that you're saying that solution is actually a fairly complex dynamical model.
Yeah.
It has lots of little components that all interact with something.
Yeah. At least that's my viewpoint. I might be wrong.
Sure.
But my viewpoint is that, this is what everybody's doing in any kind of science for half a century at least, except in economics. You see? I mean, in standard economics, we are the unique discipline I'm aware of where people still think in a completely static way. Why? Because we are stuck with the old models, the old paradigm of the 70s. At the end of the 19th century, at this time, I mean, in physics, people had Newton and differential equations, but economists were not aware of that or not. So, and Poincaré was just beginning the topology of dynamical systems and these kind of things. So economists at this time, they started with a completely static model. But the unfortunate thing is that they didn't move from that, apart from Stephen Smith, who tried to do something, but we didn't have any empirical background. So it remained a purely ethereal, theoretical attempt.
So you got us stuck too. Just a couple of days ago, explained to me
Yeah.
Now
He's gotta go back to his classes.
Yeah. So you had a question over there.
Yeah, so this is a more difficult question, I guess, for one that doesn't have a concrete answer, but then how do you get the discipline of economics to adopt changes? And how do you translate those changes into policy?
Yeah, so to be honest with you, it's far from easy because there are a number of beloved colleagues who don't want to change. I mean, they have been trained in a paradigm and they are teaching this for years, decades, and they have published hundreds of papers using this kind of paradigm. A few of them are honest enough and clever enough to say, well, what I did was wrong. One of them is Joe Stiglitz. So the guy who got the Nobel Award at Columbia University, he's quite supportive of these kind of models, even though he never worked himself on that. And he got the Nobel Award for completely orthodox neoclassical static models that he wrote in the 80s. But he's honest enough, and now, he's safe and confident enough. He has nothing else to prove. He can say, well, this was back then at this time, it was the best I could do. And nowadays, I think what Giroud's team is doing is the best we could do. He said it. Another example is Paul Romer, who was the chief economist of the World Bank. So I presented him to him a couple of years ago. I was still the chief economist of the French European Bank. So as chief economist, we would have discussions, with coffee and all this. And so you may have known that he was in trouble with his own team. So most managers of his research team were there in the room. And he said, oh, Gaël, that's what you're presenting me is very clever. We cannot do this at the World Bank. It's too clever for us, which was a provocation against his own managers. And he got fired 1 year later. Yeah, he's the unique chief economist I know who was fired by the World Bank. And he got the Nobel Award 1 year later, which was, which backfired against the World Bank, for sure. So there are struggles, there are, tensions among ourselves, because obviously some of us don't want to change, for obvious reasons. So what I did is, that's why I accepted to take the position as the chief economist of the French European Bank, which is not an academic institution, but which is an institution which deals with economics, with governments, and tries to, implement, to have impact on the field. So as a chief economist, I could say, I talked to Vietnam, the Vietnamese government, Morocco, pre-Bolsonaro, Brazil, etc., etc. And I could say, I think most models that we use are completely nuts. But if you're interested in, we could build other models that could help you. And to give you just a very simple example, which is Vietnam, to my own surprise, this was very successful. That is, those governments, they know that economists are useless because what they're telling you is just, everything is at equilibrium. Whatever is happening, you will go back to the previous equilibrium, like in Greece. They know that's not true. So they don't rely on economists, actually, or just for a few. The classical models are true for the next 6 months or 12 months, unless there is a big financial crash or a war in Ukraine or a pandemic, but otherwise, because of the inertia in economy, of an economy. They don't rely on economists, to be honest with you.
How will you go about business?
Oh, they try to, they talk to each other as they did in old times. But they don't honestly, for the main big decisions, they don't rely on economists. So what Vietnam told me is that, look, the Mekong Delta will be underwater because of the rise of the sea level before 2050. And the Mekong Delta on the southern part of the country is the place where the cultivars rise for the entire country. And today you have 80 million people in Vietnam, but there will be 150 million before 2050. And that's a food security problem for the entire country. So they told me, if you can help us understand how to slow down the pace at which the Laguna is going down, and how we can transplant rice elsewhere in the country, and what the macroeconomy of Vietnam could look like with these tremendous changes in one generation, then you're interested. So that's what we try to do with my research team at the French Open Bank. And I know now I left before I saw the end result, but I know they are very happy because they are really working with Vietnam on this. But if you use a standard economic equilibrium model, you cannot address these questions. They simply do not exist, you see? So this is to give you an example. So I had to take the stand from the academia and to have another position, which is still acknowledged by the academia, but which is not an academic position. And now I'm coming back into the academia, but with another legitimacy given by the fact that I worked on the field with countries and all these kind of things. And the kind of models I was describing you, I'm trying to quote unquote sell them both to big companies. So Deloitte, the consulting company, wants to have an access to these models for its clients, and also a number of countries. So we are now discussing with Benin in Africa, Bolivia, and Chile, because the three of them want to have a national version of this model for their own purposes, which is clever.
Nimai wanted to ask, would you support or not support a carbon tax in response to climate change?
Oh, yeah, definitely. So I can just advise you to read the report written by Stern and Stiglitz. So Nick Stern and Joe Stiglitz, I contributed to this report, and the end conclusion is the carbon tax is really the best tool we have in terms of public policy to provide incentives. Now, of course, there are two caveats. The first one is that you need the big companies not to have any exemption. To give you an example, in France, we have a carbon tax, which is not very high, $40, €40 per ton, but a big oil company like Total is exempted. So it makes no sense. So first, no exemption. And second, you have to accompany socially a number of households which will be penalized by this carbon tax. That's why we had the yellow vest in France. And that's why it's becoming a problem here in the US, because you have a number of people who cannot survive without any car. And the oil is a big part of their own budget every week. So gas, So, but that's, to a certain extent, that's easy and well known. We have to pay for that. I don't see any other solution. But that's much less costly to pay for quote unquote poor households than to try to avoid the carbon tax and then to have to face the mess that we will have to face if we don't move in this direction.
Any other questions? This was an incredibly exciting talk. So please thank our speaker.
Okay, thank you.
I really enjoyed this is my old.
Oh, thank you.
Yeah. How do you pronounce your name? Giraud?
Giraud.
Giraud, that's
Yeah.
But this is my older one.
Okay.
And I like to receive your material.
Okay. I can
It's
send you this one.
Right,
Good,
good,
I can do this.
Yeah.
Let me see if we have a card of mine.
That's all right.
But I would like to you.
Yeah, well, but
It was so entertaining.
Okay, good.
So, we'll be in touch. These are really well spent 60, 75 minutes.
I'm going to introduce one of the students. This
Oh,
is Samantha
that's
James.
amazing.
So
Thank you.
she's like perfectly like set up. She's the first student, but she's
Yeah.
a sort of disgruntled student. So she's doing math. And I was like, Samantha, you have to come to this talk. Because I think you're thinking, like, you were telling me about some of the same frustrations you had about economics not getting what's actually happening. And so I had her it's like, had her in office this morning, and talking about how like, there are, just looking at grad school, and said that is a possibility. There's things that are out there that use math for you like kids. You have to come to this property, as you can see, he plays with math in a big way, but it's in a different area. Like, you're set up perfectly for like this as an example of things to do. So like if there's anything that you're thinking of, like you want like cool undergrad projects, so you've got the things, let me know.
I love tons of things. So you'll be available for your project like whenever you think of it.
Oh, yeah.
So thank you.
That was really great.
Okay, thank you. I will have to think about it. And maybe to talk to two of my in the team. So what about, having lunch together, the three of us?
Absolutely.
Maybe today, so that I will have time to think about it. I will ask my team whether, I may have postdocs who have too many things to do, and they might say, well, if you have some clever, quote unquote, small hands, but clever, then they will be happy to work with you. So let me ask them, and let me think on my own. And by small hand, I by no way means it's not interesting. You see what I mean? Yeah, so we think about it.
Yeah, especially because you've pretty much done most of the econ, right?
Yeah, I have an elective requirement that I have to do, and that's it.
So she's got basically most of the background undergrad. She's not doing the theoretical stuff. She's seen groups and stuff of that sort, but she does like the
Oh, good.
So,
And I've also taken game theory, but it's
But I'm not on that. But you would be interested in working in kind of developing systems so it's just even not even describing.
Yeah.
You would be interested in that, or are you interested in coding, maybe not, you want to do math, you want to data? You will have to tell me what you're interested in.
something you could think about, like they haven't done much coding yet, or no?
I took computer science, so I can code and using Python.
Python is fine, Python is very fast.
Yeah.
It's both fashion, but very fast.
It is.
So,
I'm also, my both of my parents are in computer science, so.
you have the genetic side.
Yeah. Well, yeah.
Well, perfect.
But at the same time, I don't want you to use you as a slave to code in a daily night in the basement. So you have to do something which is intellectually exciting for you.
Yeah.
So you have to think about it. But I'm sure I can find something for you.
Oh, I'm sure your postdocs would love help.
Yeah, I'm sure. Yeah. But then I have to be careful that they don't turn you into a slave.
Yeah.
You have to protect them. No, they're very nice.
They're great. They're great. They're all, and they're kind of fun. Met some of them. They're from all sorts of different fields.
Yeah.
Like one was in physics, one was in applied math, one was in neuroscience.
Really?
No,
And he's brought them all in.
Another one, political science. Yeah, sure. No,
That's awesome.
it's a very intense team.
Yeah.
And they are very talented.
They are incredible.
Yeah.
So, all right. Well, we'll think about that.
Okay. What's your name? Tell me.
I'm Samantha.
Samantha?
Yes.
Okay. So, nice to see you.
It was nice to meet you.
Yeah, thank you.
Wow, that's great.
Okay.